And that's this expression. Because usually when they tell you, okay, suppose you have a gas of oxygen, they don't tell you the mass of each molecule of oxygen. They'll tell you the molar mass. Or you have a gas of hydrogen. They don't usually tell you what the mass of one hydrogen molecule is. They tell you the mass of a mole of hydrogen molecules, right? So then you can still figure out how fast on average the molecules are moving if you know the temperature. And from this expression here, like the RMS is let me ask you this question. Let's consider this expression here. What if we consider air? Air is roughly 18, 19%, I'll say 20% nitrogen. And another, actually it's 80% nitrogen, and roughly 20%, roughly it's like 19, 18, oxygen. And of course there's carbon monoxide, carbon dioxide, or other crap, what molecules. But just roughly, right? So if we consider the air in this room, let's just say made up of nitrogen molecules and oxygen molecules, which of those two types of molecules has a higher kinetic energy on average? Listen to the question. Which of the two types of molecules, nitrogen or oxygen, has a higher kinetic energy on average? The
Would
average
it be
kinetic
oxygen
energy.
because it has a greater mass?
Hmm?
Would it be oxygen because it has a greater mass?
So which is heavier, oxygen or nitrogen?
Oxygen.
So this one has more mass, and this one has less mass. Okay?
Is it the same?
What?
Same kinetic energy because of the same temperature?
Because what?
Because of the same temperature?
That's right. I asked for the kinetic energy. What is the average kinetic energy of a molecule? The average kinetic energy of a gas, right? Or a molecule of a gas or atom in a gas, right, is 3 half kT. The average kinetic energy is the same for the nitrogen molecules and the oxygen molecules. All that matters is the and the temperature is only one for the whole air. You don't say, the temperature is so many degrees for the oxygen, and so many degrees for the nitrogen, and so many degrees for the carbon monoxide, and so many degrees for the carbon dioxide. Oh my goodness, no, it's just one temperature for the whole thing. And the temperature of the gas is a measure of the average kinetic energy of each one of them, regardless of whether they have the same mass or not. Now, if I ask you, on average, which type of molecule, nitrogen or oxygen, is moving faster? Now I'm talking about the speed, not the kinetic energy. So which one is going to be moving faster? It's going to be the one that is lighter or heavier?
Lighter.
So which one?
Nitrogen.
So the nitrogen molecules on average move faster than the oxygen molecules. They have the same kinetic energy. So because they have different masses, they'll have different speeds on average, so that they have the same kinetic energy, because the kinetic energy depends on the temperature. And the temperature is one for everything, right? So in this, the air, right, with this rough composition, the nitrogen molecules, which are more abundant, are on average moving. On average, they're moving faster, and the oxygen molecules are moving slower. Which is the most abundant element in the universe?
Hydrogen.
Hydrogen. Which is the lightest atom in the universe? Hydrogen. And what is the phase of hydrogen at room temperature? Does it make a solid? Does it make a liquid? Or does it make a gas?
Gas.
A gas. Interesting. If hydrogen if hydrogen is the most abundant element in the universe, and we live submerged in air, how come air doesn't have much hydrogen? If it is the most abundant one. It's the most common, it's the most abundant, it's the simplest one, it's just one proton, one electron. Doesn't have to get complicated as oxygen. Why isn't there that much hydrogen?
Because sunlight.
And yes, it's the lightest one. It's the lightest gas. Lightest, as you know, the mass per atom or molecule is the smallest. So therefore, it would be the gas where the molecules on average are moving the
Fastest.
fastest. Ooh, there it is. So what? If hydrogen were part of the Earth's atmosphere, it would be the gas for which the molecules are moving on average the fastest. And so what? Remember your Phys 185 days? If I take these keys and I just let go, they fall to the ground. If I throw them upwards, they go so high. If I throw them upwards so they leave faster, they go higher. And if I throw them really hard, they're gonna go higher. And there's a problem that you solved in Phys 185 that asks, what's the minimum speed that I need to give the keys so that they go up and never come back? So they escape from the Earth. It's called the escape speed from the Earth. Do you remember the answer? 7 miles per second. From here to the beach. Roughly from here to the beach is 7 miles? Or is it not?
Maybe a little more.
In 1 second. From here to Irvine Spectrum, in 1 second. So if I were to throw them that fast, right, they would, first of all, they'll exit the atmosphere in like 2 seconds, 3 seconds, and then, they wouldn't come back. So, if hydrogen, being the most abundant element in the universe, if it was part of the Earth's atmosphere at some point, right, given the atmosphere, right, hydrogen being the lightest, even though it's the most abundant atom and, or molecule, then by now it's left. It has escaped. Which is the second most abundant element in the universe? Helium. And helium is the second lightest element, right? So there isn't much helium either. Gone. Right. The moon. You go to the moon. I mean, I've never been to the moon, but you see pictures of when maybe some footage when the astronauts went there. The moon doesn't have much of an atmosphere. Yeah, the moon doesn't even oxygen, nitrogen. No, it's not there, pretty much. So why does the moon not have much of an atmosphere? Because if it did at some point, right? Because the size of the moon, the mass of the moon, and the size of the moon, the escape speed from the moon is lower than what it is from Earth. So if it had an atmosphere, just left. And that means that if there's a rock or little rock or pebble, out there in the universe and goes to the moon, boom, as it goes into the moon, there's no atmosphere to slow it down. There's no atmosphere to, exert a frictional force in the opposite direction that the rock is moving, doing negative work on it, reducing the kinetic energy, converting mechanical energy to thermal energy. When that happens here on Earth, right? There's a rock coming back. Did we talk about meteors? So what happens if a rock comes towards the Earth and it's a small rock? Or maybe a grain of sand. What if it's coming in from outer space into the Earth? As soon as it enters the Earth's atmosphere, so here's the Earth, and I'm going to exaggerate the atmosphere. So this is, right? If a rock comes in like this, when it enters, now there's a frictional force this way exerted by air. You know, the force of air friction, the magnitude depends on how fast the object is moving through the air. And you can check this when you drive your car. Just stick your hand out the window. If you're at, you know, if it's in the parking lot and it's not windy, you don't feel a force on your hand. But you start driving on the street, stick it out, and then, you know, your hand gets pushed, you know, by air friction. And if you do that on the freeway, whoo, it really goes back, right? So the velocity is this way, right? That force is going to give it an acceleration this way, so it's going to slow down. Kinetic energy is going to drop, and that kinetic energy, the work done by the frictional force is being displaced this way, but the frictional force is in the opposite direction of the displacement, so it does negative work. The angle between them is 180 degrees, right? Right. So the point is that mechanical energy gets converted to thermal energy, and the rock heats up to high temperatures. And what happens when it reaches high temperatures? It glows. And so what you see is this, you know, when it goes like this, or well, most likely it's gonna come in and hit the earth. Well, not you, not me, but you know, hit something, right? In most cases, those rocks are about the size of a grain of sand, like at the beach. And they burn off completely before they hit the ground, which is good, right? If they're pretty big, then they can make it to the ground, and if you collect it, it's a meteorite. When you just say it like that, and then it's, you know, it doesn't make it to the ground, it's a meteor. So for us on Earth, most of the meteors, right, you know, they're called meteors because they don't make it to the ground. If you collect it, take it to the museum, you call it a meteorite. But most of them just burn in the atmosphere. And you see this very short duration streak of light. Oh, make a wish, you know, and people call them falling stars, but they're not stars, they're right here, you know. On the moon, you don't have the atmosphere, so it just comes in and boom, hits, and throws some dirt around and makes a little hole. We call it a crater. Right? You go to the moon as an astronaut, and you put your footprint, right? That's my footprint, you know. And it'll be there for ages, because you don't have air over there or some atmosphere that's going to rain and, you know, cover it with some liquid, or something, some wind is going to be blowing that's going to throw dust on it and cover it. Now that footprint is going to be there for a long time, unless somebody else comes along and says, I don't want the foot, I just want mine, you know, and it just covers it. But the moon doesn't have an atmosphere. Why? And if it has, it's insignificant. So why doesn't it have an atmosphere? Because the gravitational speed, I mean, the escape speed from the gravitational pull of the moon is lower, so they just escaped. Right? On Earth, well, why do we not have much hydrogen, helium? Well, they will be the lightest ones. So, I mean, from just analyzing this expression over here, right? The lighter molecules will be moving faster. And by now they have reached speeds greater than the escape speed from the Earth, and they are gone. The heavier ones, oxygen, nitrogen, they're still around. They're heavier on average, they move more slowly, they don't have enough speed on average to leave the Earth, which is good for us because we need oxygen to be able to survive, right? So, this formula over here, right, can be used to explain why, you know, the moon doesn't have an atmosphere, why the Earth atmosphere is not made up of much hydrogen or helium, right, or rather the heavier ones, right? Of course, you gotta make a connection between the fact that the hotter the gas is, the faster they move, but also you can express it like this, right? You know, on average, they're gonna be moving more slowly the heavier they are. And if they move more slowly, the heavier they are, like nitrogen, oxygen, then they don't reach speeds greater that would exceed the escape speed from the Earth. Yes? Anyway.